I have been playing Tomodachi Life Living the Dream with my friends, who are all math-brained people, and this particular wallpaper caught our collective eye. This is called the Eureka set. Knock knock. Who's there? Eureka? Eureka who? Ugh, Eureka onions, I'm leaving. There are many formulas here, and I don't blame you if your first question is this slop? Fear not, my Tomodachi, all of these formulas are real, and I'm going to explain them all. Unlike this mug I have, which has gems like 6 over 275 plus pi over z-axis, n is greater than equal to beard, and the most profound expression there could be, 48,000 over women. Truly a work of genius. Okay, let's get back to Tomodachi Life. Fair warning, all of the pictures that I'm going to show you will be blurry because it was hard to capture them. So I'll do my best to provide a more readable version of the formula by either rewriting it or copying it from somewhere like Wikipedia. We begin with a nice little appetizer of classical physics formulas. Here we see Newton's formula for gravitational force between two objects. Gravity. G is known as the gravitational constant, whose value is roughly 66 trillionth. That is a tiny number. And it tells you that the gravitational force is really weak. M1 and M2 are masses of the objects in kilograms, and R is the distance separating them in meters. A force proportional to mass 1 and 2, and inversely to the distance between them squared. Then we move on to Rayleigh-Jean's formula for blackbody radiation, which laid the foundation for quantum mechanics. You know how a hot electric stove emits visible red light and infrared, that is heat? Well, all hot objects emit light of different wavelengths. If you want to talk about how brightly an object is emitting, the answer will depend on your exposure time, your angle, your distance from the source, and what filters for wavelengths you're using. Like the stove is emitting a lot of infrared, but you can't see that with your eyes. The spectral radiance B lambda is defined so as to account for all of these factors and get a sense of the power distribution of the whole spectrum of light emitted by an object. I'll link to a post that better discusses this notion in the context of photography. Here C is the speed of light, K is the Boltzmann constant, T is the temperature of the body emitting the radiation, and lambda is the wavelength we are finding the spectral radiance at. Continuing to make light of this topic, these equations express the energy of a photon with a given frequency. E is the energy, h is the Planck's constant, and nu is the frequency. You also see this f here, which again is denoting frequency, but now with a different variable for some reason. Lambda is the wavelength of the photon, and c again is the speed of light. These set of equations are deriving the energy in terms of wavelength if you know it in terms of frequency. This is the only derivation in the Eureka set, so I will overlook their sloppiness with notation. Hey, we now have a fun little diagram of Carnot's engine. The T's are temperature, and H stands for hot while C stands for cold. As heat moves from a hot object to a cold object, it is possible to harness this heat to perform work. In fact, if you run a Carnot's engine in reverse, that is, you do some work, you can actually transform from cold to hot. This is what refrigeration and air conditioning is. The formula on the bottom tells you how the entropy changes with the addition or removal of heat from the system. How much the entropy changes is dependent on the temperature. Entropy can be roughly understood as recording which configurations of particles within a system are most likely to occur. Oh, this next equation says subscribe equals u plus awesome? I wonder what's that about. Okay, so enough with these worldly considerations. Let's make our way to the stars. First, we have the equation for stellar parallax. This equation helps us find how far stars are by observing how they move from our perspective. You have probably done this when you were a kid. Closed one eye and held your thumb at an arm's distance. Then close the other eye while opening the previous one to watch your thumb jump to the other side. Maybe you did this a few times, seeing your thumb perform this trick of teleportation while the background remained fixed. After a couple winks, you open both of your eyes to find yourself a full-grown adult, teleported into this very stressed body. But hey, imagine your thumb was a star. When things are so far, they move very little. Your two eyes correspond to the 2 points on the opposite side of Earth's orbit. How's that for a pickup line? With a little bit of trigonometry and using the small angle approximation, we can derive this formula. P is called the parallax angle as shown in the picture, and the d is the distance to the star. The one in the numerator has units of astronomical units, where one astronomical unit is the average radius of the Earth's orbit. And here's Hubble's law, which says that farther away galaxies move away at a faster rate. Here v is how fast the galaxy is moving away, and d is the distance from us. h0 is some constant parameter which dictates how fast the galaxies move away. Okay, we have looked at a bunch of formulas, so here's a picture as a palette cleanser. Here we see a model of light cone in special relativity. The idea here is that the observer in the center can only receive information from objects within its past cone and can only send information to things within its future cone. There is a nice video by Floathead Physics that uses the idea of light cones to explain why we age slower when moving really fast, or why fast-moving objects get squished. You can put numbers to the two changes I described by using these equations called Lorentz transformations that appear in special relativity. If I am traveling at a speed of 50 miles per hour and you are traveling at a speed of 60 miles per hour, then from my perspective, you would actually look like traveling at a speed of 110 miles per hour, which is the sum of our speeds. This is why when you pass a moving train on your journey going the other way, it looks like it's going really fast. When going at speeds close to the speed of light, the speed of things moving opposite to each other don't add this way. This is because the max speed in the universe is the speed of light. So the length and time have to change in order to respect the speed limit. Here this letter gamma is dependent on your speed and tells you how the length and time are affected for you. As we are on the topic of relativity, here's the most famous equation of all time, E equals mc squared. Energy is mass, mass is energy, this is the speed of light, please do not make bombs. Back to our regularly scheduled programming. We are back on Earth, and to my surprise, we find a bunch of machine learning related topics. So let's talk about them. We first have the Heaviside function, which is 0 for negative values and 1 for positive values. This function is named after a guy, but it's a pretty apt name as it's heavier on one side. This function models an object, like a neuron in a neural network, that is on for a certain range of inputs and off otherwise. This transition from 0 to 1 can be pretty jarring, and in real life things are much smoother, like the segue that brings us to today's sponsor, Masahiro Sakurai. Thanks Sakurai for making all our favorite games such as the Pink Demon, Beat Your Friends, Fire Emblem, and Seizures on a Plane. Use my code POYO to get 99% off. Now back to the video. Here we find the logistic curve which corrects the sins of the Heaviside function by making the transition from 0 to 1 much smoother. It is close to 0 for highly negative values and close to 1 for large positive values. This more accurately models neuronal output and is also useful in modeling the rate at which a population with limited resources grows, or any other phenomenon that shows saturation behavior. As this logistic curve is getting comfortable in being the better function, it is dethroned by the softmax function, which generalizes the logistic function to multiple inputs. In statistical mechanics, lower energy states are more likely, and the likelihood of such a state occurring is given by evaluating the softmax function on it. This is also called the partition function. This idea of a softmax function is useful in machine learning too, as it assigns a smooth probability distribution to possible output values. Ooh, now we find the poster child of machine learning. This is the ramp function, or the ReLU activation function. It is 0 for negative values and increases linearly for positive values. This allows us to scale the output according to the strength of the input. Think of the Heaviside function as a digital output like a D-pad, and the ramp function as an analog output like an analog stick. Spanning the top of the walls are these long equations. These are the equations for Q-learning and reinforcement learning. If you're training a machine through work-through situations, it will start taking some actions to resolve those situations. If you've just started training, the action might not be useful in that situation. So when an agent is learning, it records the quality of an action A for a situation S using this function Q. These equations update the value of Q for a given situation and an action based on the reward obtained, and thus the agent learns. Also, I'll be real with you, these are so hard to get a picture of because the camera in Tomodachi Life does not pan upwards. Also, these are only visible when you put the wallpaper in the living room. Okay, it's time for a shadow quiz. What is this object? Did you guess the ramp function? Let me know in the comments if you won. Our last category is miscellaneous math stuff. This picture is of a square pyramid and the formula next to it is computing its volume. Then we have two equations in different spots on the wallpaper defining the golden ratio. I would have expected one of these to contain the Fibonacci spiral at least, but whatever. If a and b are Fibonacci numbers, then by definition the next Fibonacci number is their sum, a plus b. If I write the Fibonacci sequence and list the ratios between the consecutive entries, you will see that the ratios converge to a certain number. This is what we call the golden ratio. This equation is not only redundant, but also like there's no C anywhere. Do you see it? Cause I don't. Enough with the bad stuff. Here is one of my favorites. The story goes that Ramanujan was sick in the hospital. Hardy, his mentor, walked into the room to check on him, and in order to cheer him up, Hardy claimed that he saw a taxi cab with the most boring number, 1729. Ramanujan perked up in vehement opposition. This is not a boring number at all, he said. 1729 is the smallest number that you can write as a sum of two cubes in two different ways. The two ways being 12 cubed plus 1 cubed and 10 cubed plus 9 cubed. It is due to this legend that we call these numbers taxi cab numbers. There is also evidence that Ramanujan didn't come up with this fact on the spot, but rather knew about it. He had connected this number to objects called elliptic curves previously in his notebook. This little equation here calculates the area of a triangle with base length b and a height h. The last two remaining entries I'm a bit iffy on, so I would appreciate any ideas you guys have. Here is an ellipsoid, basically an egg shape. The equation on the side is summing the semi-axis of ellipsoid, I think. Why is this quantity significant? I do not know. The next one is even more troubling. This formula approximates the value of pi using a convergent series. These websites are attributed to Ramanujan, but I cannot find a good primary source for it. If you know one, I would love to hear it. Hopefully you learned something today, or had a fun time, or both. This kind of video is not my usual fare, as I mostly discuss math topics and academia stuff. Please check my other videos out if you like this. Bye bye.